Hi friends, welcome to our channel. In this video, we are going to look at today's daily challenge problem, valid triangle numbers. So this problem, the statement is very short and brief, while the method is very typical. So here I'm going to use two-pointer sliding window. So the problem asks us, given an integer array called nums, so we want to return the number of triplets chosen from the array that can make triangles if we take them as side lengths of a triangle. So here we have two examples. In the first one, the return is 3. So it lists the 3 triplets. And in example 2, the output is 4. We are going to quickly analyze this before we do the coding. So here the constraints are the following. First, the length of the given list is bounded above by 1000, and the numbers are non-negative numbers, right? So here one thing is that if your nums I is the length is 0, so you cannot form any valid triangle. So here in this regard, so you can use some pop operations logically to make it complete, right? So here let me first explain 2 points. First is that we can do sort, right? Because we need to find all possible triplets. No matter we sort or not, then the total number would be the same, right? So this is the one point you need to realize. So the second point is that we can fix the longest edge C. Then the 3 numbers A, B, C form a valid triangle. Mean is equivalent to C. A plus B is greater than C. So here is strictly greater than C. And then once you realize these 2 points, we can use two-pointer sliding window to get the number. So this is the walkthrough for example 1, because in the left side, the explanation lists the 3 triplets. I will not go over here. So I'm going to use example 2. So here, after sort, you get 2, 3, 4, 4. Then you can loop from the backend to the beginning. So for the last 4, right, at index 4, you can have 2, 4, and 3, 4, and 2, 3. This gives us 3 triplets. And for the second index, so you can only use these 2 numbers, but they do form triangles because 2 plus 3 is greater than 4. Therefore, this is another triplets, right? So here by triplets, I mean this 2 tuple plus the C, right? So when you look at the C here, so you don't have enough numbers left. Therefore, you cannot contribute to more triplets. So that's the quick walkthrough for this problem. So now let's quickly look at the coding, right? So if you have practiced quite a lot, so you will quickly realize the pattern for using two-pointer sliding window method. So here first I'm going to sort this one, right? And then what we are going to do, so we initialize an answer. So this is a counting variable. We are going to return its final state. Then I'm going to iterate over for say I in range, so length nums. So here I can end at the index 0, or I can end at the index before index at index 2, end at index 2. So here let me say again. So because we need at least 3 numbers, so this I will correspond to the C here. So this index cannot be smaller than 2. If it's smaller than 2, you don't have enough numbers left. Therefore, you don't need to iterate. But this is a small point. So here, let me see. I'm going to use L to be the 0, right? And R to be the I minus 1. So in other words, we are going to use this nums at index I to be the last number. So basically the check will be the following. Well, L is less than R, right? So if nums L plus nums R is greater than nums I, right? So if this is the case, then every number starting from L, so starting from L and ending at R, so comma with this current index I, will form valid triplets. So how many L's? It's from L to R minus 1. So from L to R minus 1. Therefore, the count will be R minus 1 minus L plus 1, right? That is nothing but R minus L, right? So here I'm going to write, so the answer is incremented by R minus L. So if this is the case, right? So then what we can do, so we can try the second number, make it less, so we can make R minus 1, right? So this is the one case. Another case, if this is less than or equal to nums I, so then in this case we need to increment by 1, right? So this will give us the counting. So afterwards, so we're going to return the answer. Let me first do a test. Index out of let's see, out of range. Let's see, answer equals 0, L less than R. If nums L plus nums R is greater than, then answer will be this. So let me write like this. Answer will be answer plus R minus L. Then here R minus 1, else L plus 1. I guess this should be okay. List. So after we sort, answer length. Oh, so here I guess this this index list should be minus 1, right? So for a array of length n, the largest index will be n minus 1. Now let's run it. So this small scale you need to pay attention to. So it passes the 2 test cases. So now let's look at the generic case. It passes all the cases. So now let me make some comments. First, the iterate range. So because here we need at least 3 numbers. So we can stop. Say here, the smallest I should be index 2, right? So we can stop before index 1. So this should still work. Yeah. So we can stop before index 1, right? So that's the one part. Another part is that by the assumption, so the numbers can be 0. By assumption, nums elements can be 0, but our code takes this into consideration already, right? So here, after we this is due to sort, because we have sorted one, so each time we see the last one, so this is the largest possible, right? So if the largest possible is 0, and then all the previous one is also 0, it's impossible to have this condition, because 0 plus 0 will be 0. Or if the current largest edge corresponding to index I is not 0, but the previous one is 0, for example, the L corresponding to element 0, then it's impossible to have nums L plus nums R is greater than this one. Because if this 0, it reduces to nums R greater than nums L. But we have sorted, right? Then nums R should be less than or equal to nums I, because the index R is smaller than index I. So this is the one point, right? So if you want some redundancy, so you can use pop, but it's redundant, right? So you can see, well, nums and nums and 0 equals 0. So here you need to pop. It will be good to make it the pop left operation to be O1. So you can do something like nums equals collections dec nums, right? So then you can do nums pop, right? So this still works. So here, let's see. Here, I guess what's the problem? So here, once you pop that, so let's print this. Print this nums. So used as test cases. So I guess for this, if you run it, so sort the deck will be nums and nums, so not nums 0 equals 0. So we do pop. So here, let's see, the deck shouldn't be 0. Let's see. Nums collection nums deck. Let's print out here. Yeah. So here, nums and nums 0 equals 0. So we're going to nums pop, then print num. So why it becomes 0? Let's see. No, why it comes to so here, not pop as pop left. So here, that should work now. So yeah. But as I mentioned, so this 3 lines is redundant. But if you realize these lines or these details here, so actually you have a better understanding about the coding, right? So in other words, the code is very short, right? So if we don't include these 3 lines, it's just like a 3, 9, 3, 6, and then 11 or 12 lines of code. But it includes a lot of logic here. So I guess this also tells us something. So when you analyze the code, you need to really understand the details besides the big picture. Both are very crucial in order to really digest the problem and the coding. So with that said, I guess that's it for the current problem. Thank you for watching.